Okay, so today's lecture is a continuation of these determinants, but now we will use a method that is actually much quicker and less prone to error than the method from the cofactors, as we introduced determinants on 2.1. But it relies on, as the word says, row reduction. And as I said, some of you seem to have still problems with row reduction. So please, this is so important. It's not just this topic, it's the quiz on Thursday uses row reduction. It's the next topic is use row reduction. We're going to be using this all the time. So if you don't understand row reduction, go back, look at the videos that I have, or go back to your notes and read the textbook. All right? Okay, so our goal is to calculate the determinant, but not via cofactors. Okay, and let's I'll start with an example. So suppose my matrix A is here, 0, 1, 5, 3, minus 6, 9, 2, 6, 1. Now, before I actually explain the method, well, let's do at least use our previous method to see what the determinant is. Remember, the determinant A, I can expand this choosing a row or column I want. I'm going to use at least this. I want to make use of this 0, so let's say I'm going to use row 1. That means that there are two elements that I have to look for, this one and its cofactor, and this one its cofactor. Also remember we have signs, so the signs here will be plus, minus, plus, right? So this first one comes with a negative sign. We get -1 times what is left. Well, we scratch out these two and we see 3, 9, 2, 1 is left. 3, 9, 2, 1. And then we have this factor with a plus sign, so plus 5. And the cofactor is now scratched out and we find 3 minus 6, 2, 6. Right? Okay, so we can work this out. It's -1, 3 minus 18 plus 5 times 18 minus 12. That is -1 times -15 plus 5 times, that is 30. So that is minus is plus 15 plus 150, that is 165. All right. So we know what the answer is going to be, but and you see it's actually not that bad, right? But the more columns and rows you would have, and also the more non-zeros you have, the harder it becomes to use this method. And the following method with rows and row reduction will become much faster. Okay. So let's look at our matrix again. So we want to calculate the determinant of 0, 1, 5, 3, minus 6, 9, 2, 6, 1. Okay. And we're going to do this by row reduction. But to do this, well, what we would do is we look at this matrix here and we say we have to row reduce it. And you see what we're going to do is we go again to echelon form, not the reduced one. So it's only the first phase that we have to worry about. You'll see why. Okay, let's start figuring out what to do. Well, the first problem is that we have to have a pivot here and it's a 0, so we have to move something. But we don't have a 1. But actually we see that we do have a 1 here. Look, here I can make this a 1 by dividing everything by 3. And I would have a 1 here, and then I can switch the 2 and I would have a 1 where I want. Okay, of course I could first switch and then make the 1, whatever you want to do. Let's do making this a 1 first. Okay, so I would divide, so the row operation that I have in mind is replace row 2 by 1/3 of row 2. But this is now the thing. So we're going to use row operations But unfortunately, they're going to change the determinant, okay? And so what happens is, if we divide by 3, we're going to say this, this is the same. Let's see what I will do. How does the determinant change if I divide by 3? Well, the change will be that I'm going to think of this in a different way. I'm going to say I can factor out a 3 here of this row, and I'm left with 0, 1, 5, 1, minus 2, 3, 2, 6, 1. Now, this is very important, and this you have to be very careful. Notice that I only divided row 2 by 3, or I factored out a 3. Only row 2. That is not the same thing as factoring out a 3 out of the matrix. So there's a difference between what we do with the matrix and the determinant. Here we're talking about determinants. Right? I remind you, just if you would do 3 times the matrix, 0, 1, 5, 1, minus 2, 3, 2, 6, 1. 3 times would mean every single number has to multiply with 3. So the result will be this matrix. Which is not the original matrix. So you see, it's a different thing. Taking out a 3 out of a matrix is different than taking out a 3 out of a determinant. In a matrix, you do everything. In the determinant, you take a row. In fact, you can also take a column, but I want to focus on rows here. So we factor out a 3 out of one of these columns, and that row, sorry, and that is a valid operation. So when we do a row operation, this row operation now amounts to factoring out a 3. So, okay, there's 2 ways of saying it, right? I'm saying I'm dividing this row by 3, that's the new row I get. But I can perhaps better say I factor out this factor 3 out of row 2. Okay, so how do we proceed now? Okay, let me go back to my black comma. We have now the one that we want. But it's not in the right position yet, so we have to switch it. Okay, so let's do that. So I'm going to switch this. So the row operation that I have in mind is, let me write it, the next row operation. So this was the row operation for here, right? So now, what is the row operation for this step? I'm going to switch row 1 and row 2. Okay, so we have 1, minus 2, 3, 0, 1, 5, 2, 6, 1. That's the result of switching. So I should have done it in black. That's the result of switching, right? These 2 rows. Now let's see what we have here. The 3, of course, we have to copy that. But we're doing something here again. When we switch, we also change the determinants. When we switch 2 rows, the sign of the determinant changes. So we get a minus sign. So this minus comes from the switch. Now before I go on, I want to show you why this is the case. And let's do this on a simple, let's look at the one of the elementary matrices that you get by doing this particular row operation, so the switch of row 1 and row 2 on the identity matrix. So we have our identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. And if I do this row operation on the identity matrix, I get the E that I want. So E will be, for now, my example will be, well, just change 0, 1, 0, 1, 0, 0, 0, 0, 1. So this is the elementary matrix. We discussed this a little bit earlier in chapter 1. And why do I bring them even up? Well, applying this row operation to any matrix is exactly the same as multiplying that matrix with this guy. Okay, so let me write. So if I have a matrix A and I do this row operation, I get a new matrix. Let's call it B. So for instance, here's the example, right? This was my A, and I do the row operation and I get this matrix B. Okay? If I do this, remember, that is the same as saying that you actually multiplied A with this E here. This E that what is this E? Well, apply the same row operation onto the identity matrix, and that gives you the elementary matrix corresponding to this row operation. And I did this here for the switching, but this is true for all row operations. Remember this? Okay. So, right. So what we see is that if we replace A and we do row operation, we get a new matrix B that's the same as multiplying with A. And now there's a very important property, so there's a theorem if you want. The determinant of a product of two matrices, let me call them something else. Suppose we have two matrices M and N. That's the same as the determinant of the first matrix times the determinant of the second matrix. We'll come back to this, but I'm using it already. Okay? So in this case, this would mean that the determinant of B is the same as the determinant of E times the determinant of A. Now let's look at what is this determinant of E here. We have E, right? We don't know A and B because this was for any A. We will go back to our example, but now here, this one, E. What's the determinant of that thing? Well, let's work out this determinant using just cofactors. And being smart, because we have a lot of zeros and so in fact, it doesn't really matter what you do here. So let's take row 1. Okay. Now row 1, that means we're talking about this element, but look at the sign, it's a negative sign. So I get negative 1 times, scratch out what you left, and you're left with 1, 0, 0, 1. That's a 2 by 2 matrix, which you just multiply, work out. And this, of course, easy. That is minus 1 times 1, so negative 1. So the determinant of this row operation, of this elementary matrix, is negative 1. Which means that, if I plug this in, that the determinant of my new matrix is minus the determinant of the previous matrix. And so that's what it means. If I switch two matrices, then you switch the sign of the matrices, of the determinants. And that is exactly what I got here. This was my A, right? And this is now my B, and the difference is a negative sign. All right? So that's the result of this operation. Now, I invite you to do the same thing that I did here with another row operation and see what happens. Okay? I will do this in a sec in the next step. But you should also try it for this one and see that's exactly where this tree comes from. But okay, let's move on. Let me erase the part below here and then go back to our calculations, because we're not done yet, right? We have now a 1 in the right spot, and we can now do a row operation that takes care of this guy here. So the row operation is now row 3 replaced by row 3 minus 2 times row 1. Agree? Okay, so let's write down what happens inside. Nothing here, nothing there. The only thing that we changed is here, the third row. So we do minus 2, so we multiply this with negative 2 and add to this row. That is a 0, of course. Minus 2 times minus 2, that's 4, plus 6, that's 10. Minus 2 times minus 2 is 4, plus 6 is 10. Minus 2 plus 3 is minus 6 plus 1 is minus 5. Okay? And then we also had this guy, minus 3 here. But now is the question, what is the effect of this row operation? When we saw what can happen when we factor out something, the factor comes out. When we switch, we get a negative. What does this do? The good news is it doesn't do anything. Why? Well, let's look at this particular row operation and do again what we did here with our elementary matrices. Okay, so I'm doing this now. A temporary. I suspend a little bit my calculations and go again. So we're talking about the row operation, row 3 minus 2 times row 1. Okay, so if I do this on the identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1, then I get the new matrix that I get is the two first rows don't change, and then here I subtract it twice, so minus, let's say it wrong, right, sorry. So multiply with -2 and add there, okay, right, so we have a -2 here, a 0, and this of course is a 1. Okay, so we have now this thing. So that is our new elementary matrix E, and then the thing is that if you take a matrix A, you carry out this particular row operations, you get a new matrix B. That's the same as multiplying your old matrix A with this E. And then we have the rule of determinants, that the determinant of A is the determinant of E. Sorry. I'm looking at this formula. The determinant of B is the determinant of this guy, which is the determinant of E times the determinant of A. So everything is again, what is this determinant? Well, let's work it out here. We have to calculate the determinant. I'll write it up here. 1, 0, 0, 0, 1, 0, minus 2, 0, 1. You can actually immediately see that it's 1 if you remember from previous lecture upper triangular matrices as well as lower triangular. This is an upper triangular matrix. Have the determinant is just a product of the diagonal elements. Okay, but okay, if you forgot this, then no big deal. Let's work it out. Again, I'm going to do row reduction. Row expansion, row 1, because I have only one. These two guys are 0. So, and the sign is now, of course, a plus sign here. Okay, 1 times, and what is left? Well, this guy. 1, 0, 0, 1. And now you see already that this is also 1, right? 1 times 1, so the whole thing is 1. So, right, so this determinant is just 1. In other words, if I start from a matrix A, I do a row, this type of row operation on it, I get a new matrix, but the determinants are the same. That's the good news. In other words, if this happens, I'll go back into our example that we have. If we have, we did this row operation here, from here to there, right? We did this row operation. Nothing changes. So we have still this -3 outside, and we have now the new matrix. Okay, so we can keep doing. We have now our pivots, 1 on 1. The next one is this guy, right? Okay, let's do it. That's the row operation we need. I hope everyone sees it. Row 3, replace that by row 3 minus 10 times row 2. Using this pivot to make this 0. Okay, so the result is, let me go back in black, the -3 that we had, and then we're going to get a new determinant, but since it's again a row operation of this form, nothing changes. So we get 1, -2, 3, 0, 1, 5, and now, so remember we multiply this with -10 here and then add it up. That's a 0 here, we had a 0, and then here we get -50 plus -5, that's -55. Okay. Last step, well, this should be a 1, right? Okay, so this is the pivot, but it should be 1. So let's bring it out, because we divide this row by bringing it out. Now, remember, bringing out is very simple. It's really what it is. If you have a factor in a common factor in one of the rows, you can take that factor out and divide the row and leave the other two rows unchanged. So the same thing here, we're going to factor out. So the next thing I'm going to do is factor out. We have the -3. Now I'm factoring out this guy, -55. And what I'm left with then is 1, -2, 3, 0, 1, 5. And in this row I divided everything by -55, but there's only one thing left. Right. Now we have a lower triangle matrix, and we know already that the determinant is the product of the diagonal elements. But these are all ones. We are in echelon form here. Notice that this is the echelon form. That's why I said that's how far we need to go. Because we know that this thing is equal to 1, the determinant. Again, why was this? This was because if you start expanding this row, then you're left with this, then left with this determinant, and so on and so on. Okay, so we get 1, and so you see that the answer is this times that, which is, no surprise, 165. That's what we had here too, right? Okay. So let me quickly repeat. I'll write it up a little bit for you, then you see it better. We have 3 row operations. So 3 row operations. Let me row operations, right? Switching to rows, I'll give examples. That gives a factor -1. Replacing a row by some multiple of the row, by dividing the row by something like the one we did here. Sorry, no error here. Then we get a factor 3 coming out. So you have to understand what happens here, right? So dividing by 3 means that's the new matrix I get, the new row I get. But what I do is I bring that 3 out. And then finally, the row operations of the form row 2, replace row 1 plus row 2 plus row 1 plus row 2. Any of these operations, you just don't do anything, multiply with 1. Okay? Perhaps that's less. Let's do another example, that helps probably better. Okay, here's the next one. I'll do a 4 by 4 because that works too. And moreover, once I show you now that once you get the hang of this, you can actually go much quicker. Okay, I'll do this one here. Let me see. Yes, this one here. Okay, this is example 5 in the book. Calculate the determinant 3, 5, minus 2, 6, 1, 2, minus 1, 1, 2, 4, 1, 5, 3, 7, 5, 3. You see that this, if you would have to do expansion here, not pleasant, right? Because there's no zeros, and then you have 3 by 3 matrices left, the cofactors, and then those, you don't want to do this. But you'll see actually we will still use that method, but in a smart way. Okay, and also this method that we just described was we followed it to the letter, so to speak. We really did what we needed to do, and we ended up with the echelon form here. But we're going to be a little bit smarter about this as well. Okay, let's see what I mean. Well, if I were the echelon form, I should make this a 1. But I'm saying, okay, I have a 1 here. Can I not work with that one? So be careful, right? What I'm now explaining works for determinants, but it will not work for like row reduction solving system of equations. Okay, don't mess up the methods. Okay, so I'm going to use this guy. To what? To make zeros everywhere else in that column. So this, all of these I want to make zeros using this one, as if it was on top, but that's the one step I skip, because switching brings in this negative signs, and I want to avoid that, although you'll see the negative signs will come. Okay, let's do this. So let's write down one of the row operations that I'm planning therefore to do. Well, first of all, row 1 I'm going to replace by row 1 minus 3 times row 2, right? If I do this minus 3 and add it up here, then I get 0. Okay, then row 3 will be row 3 minus 2 times row 2. Remember, I'm now working with this row 2. This is a bit unusual, but I do this. And then finally, row 4, I replace that with row 4 minus 3 times row 2. Okay. And none of these, remember, do change the determinant, so I can really write that this is equal to the determinant that I get by doing this now. Okay, so this times minus 3 plus that, so I get a 0 there. 2 minus 3, that's minus 6 plus 5 is minus 1. Minus 3, that's 3 plus minus 2 is 1. Minus 3 plus 6 is 3. Okay. The second row is the one that I'm working with, so nothing changes there. Now here, multiply this guy with -2 and add. So that would be a 0. That also gives me a 0. This is -2, that's 2 plus 1 is 3, and that is -2 plus 5 is also 3. Okay, and then finally this guy, to get this one, I did this operation, so I get a 0 there. I'm going to have to multiply again with -3, right? So this is with -3. This -6 plus 7 is 1. -1 times -3, that's 3 plus 5 is 8. And -3 plus 3, that's 0. No, I made a mistake. No, that's correct. That's correct. Okay. And I repeat, I'll write it here, equal sign. It was a bit weird to write it there, but let's write it here. Why are they equal? Because these type of operations do not change the determinant. Now, see, this is where I'm going to play smart. I was doing row reduction, but I said, but wait, if I have a matrix like this, I should now use expansion along which column or row? This one, of course. So now I'm switching to the column 1 expansion, and I'm not doing row operation. Okay, let's see what do I get. First of all, signs. This is a plus, and then this would be a minus. So we have a minus, right? So it is minus this number 1 times what's left. Well, scratch out what is left, and we have a minus 1, 1, 3, 0, 3, 3, 1, 8, 0. Okay. Good. At least we have now a 3 by 3 matrix. Because it was annoying, right? When we were doing this, we had to keep writing always 3 by 3 matrix. And you'll see this technique makes the writing more compact. But again, now I don't have enough 0 rows. So if I don't have enough 0 rows, I'm going to do row reduction. Okay? I can use this pivot, but now getting the hang of it, I don't need to use the pivot in the top row. I can use any pivot as long as it's in the first column at least. Well, and even that's not necessary. But okay, I'm going to go now with this pivot instead. And therefore, the row operation that I have in mind is, remember, I have to make, this is okay, but I have to make a 0 there. So the row operation I have in mind is replace row 1 by row 1 plus row 3. I hope everybody sees that's what I'm doing. Okay. Again, since this type of row operation doesn't change anything, I get -1 times the new matrix that I get by doing this row operation. So what I'm doing is just adding, right? I'm just adding that to that. That is minus, adding that to that. That's a 0, 9, 3, and then nothing else happens here. 0, 3, and 1, 8, 0. You got that? Okay. But this time I made again a new column with almost all rows. So this is better to do row expansion. So now I'm going to do row expansion here. No, sorry, I said wrong. Column expansion. Column 1. I hope I said it right there, right? Yeah, I said it right here. Column 1. Okay. We have to take care always of the signs. So signs always, you see, they're very important here. Plus, minus, plus. So we have a plus sign here. Okay, so plus, I'll write it. That's this guy. I have this -1, of course. It's a bit silly that I write it this way. And then, what we have, a 1 here. That's why I want pivots, right? It makes it easy. So I times 1. And then the cofactor is 9, 3, 3, 3. Now this is a 2 by 2, and I have a very easy formula for that, right? But the 2 by 2, I just use my usual stuff. Okay, the whole stuff was just a minus sign, and then I get multiply these two, 27, multiply these two and subtract, -9, I get -18. Look, that was much quicker than doing only row reduction or only expansion. So repeat, in this method, what you do, and there are homework problems, that you work on them. I'll post the homework problems separately on the web page, the special ones and also the general ones. But let me repeat, what we do is we look 4 ones. And in this way, you can actually be even more lenient and work with any element you want, but it's safer to work from, let's say, work in that direction. Start working in row 1 always. So in row 1, we located this 1. We used this 1 to make zeros using row operations that did not change anything. Then we noticed that expansion along such a column makes it is very easy. And we repeated the process. We get again a matrix with ones and non-zero, perhaps not that many zeros, but with a 1 here that we could use to use it as a pivot to make these guys 0, so that we have a row along which we can expand. And then once we end up with a 2 by 2 matrix, you see the sizes always go down by 1, right? Once we have a 2 by 2 matrix, we are done, because we have our formula, right? I hope everybody still remembers, right? The formula for 2 by 2 is AD minus BC. Okay, so try these homework problems, and then we can go over them next time again.